we'll have to go through some of this stuff pretty quickly. So I've got my pre-written solutions over here on the right. I'm sorry about the whiteboards, that's a bit of a weird depth perception thing. And then over here on the left, I've got the exam that we can run through. I'll try and make this collaborative, so I'll reach out to you guys to see what you think about it. And then on some of the questions, I'll just run through myself. So to start off with, the exam split into thermo and heat transfer. And basically your thermo, if you haven't looked at it already, you have 3 multi-choice questions and then 1 long response cycle question. Alright, so question 1, we're given an ideal refrigeration cycle and we're basically given the 2 scenarios, like a more realistic scenario and then our ideal scenario where we have isentropic compression and we have a few correct options. This is a key part to look at. There can be more than 1 correct answer in this multi-choice values. Alright, so we've got the heat removed from the refrigerator will change. The network supplied or heat rejected will change. Ideal, an actual COP, and so on and so forth. Okay, so any ideas on what happens when we have isentropic compression? Just yell out your answer.
First, S is constant.
Are you asking if the performance increases or decreases? Is that what you mean?
Just what do you think will happen? Whether you think it will increase or decrease. Also, you can make a comment on A and B. They don't specifically talk about performance, they talk about aspects of the cycle.
I think it's most likely B and C.
Yeah, so that makes sense. So, C, B and C. So coefficient of performance follows this equation here. We're given H1, H2, H2 ideal, H3. All you need to know is that H4 in our equation here is equal to H3. And then QL is this value here. And you can see H1, state 1's always at the same point, so this doesn't change. However, when we go to state 2, we actually draw state 2 down. So our network supply decreases, and then our heat rejected decreases as well, because our state 2 comes down to here. So that's a pretty simple one. Hopefully you can get both of that. Question 2 is based on psychrometry. So here we've got a bit of understanding about psychrometry, and we want to design an air conditioning system for our house. So our room conditions are dry bulb temp of 29 degrees Celsius at a relative humidity of 40%. We aim to remove around 14 kilojoules per kilogram of heat from the air at constant relative humidity. So we've got a few statements to select from. So you'll be given your psychrometry chart. So it's this one here. Anyway, just look down the bottom. So I've already annotated it. Sorry if it's not clear to see, it's a bit easy. I'll try to print in colour. But pretty much all we have to do is I can see I've labelled T1 here. So we come along our x-axis because it's dry bulb temp, go up. Here we hit 40 degrees relative, or 40% relative humidity at 29 degrees Celsius. And from here, I can go on this angle and I find H1. And I can also go directly across and find omega 1. Because our design parameter is the drop enthalpy, I've come down 14 kilojoules per kilogram on my enthalpy axis. And then I bring a ruler to the exam. On this angle, I've come down until I've hit 40% relative humidity, and I've marked this point. When you come down, I'm just above 23 degrees dry bulb, and I am just below 8 or just above 7 in terms of my absolute humidity. So I started at 29 and I went down to 23 in terms of dry bulb, and I started at around 10 and went down to 7 in terms of absolute humidity. So from there, we know that our answers are going to be A and D. Is everyone comfortable using the psychrometry charts? So there's a bit to them. So it's a bit hard to see, but pretty much these like parabolic lines. I'll just get you to be quiet so everyone can hear me. So these parabolic lines are our relative humidity. Our x-axis here displays a few different things, but it's pretty much your absolute humidity, your dry bulb temps on your x-axis. This line up here is our enthalpy, and then this final curved line here is 100% relative humidity, or your wet bulb temp. So if you get asked about wet bulb like we did in the tutorial, you can come across to here. But also, it's very difficult to see. There's these dotted lines that run along on angles. They're also wet bulb temps, so you can determine at different relative humidities what your wet bulb temp would be. The best thing to do to get comfortable with these is just to solve questions and use them like you do with any other thing. Right, and then now we come down to question 3. So question 3's got a few different statements. Yes?
Just in case we have, can you explain me what the...
Oh, yeah. So, omega 1 was about 10 grams of H2O per kilogram of air. So you can see I went to 29 degrees wet bulb, dry bulb, came up to 40% relative humidity. If I go straight across to my y-axis, I hit about 10, my absolute humidity. This point here is where I am at state 2. I've decreased enthalpy in the air. I get my dry bulb temp, and if I come straight across, I get my absolute humidity, and it works out to be roughly 3 grams of H2O. Any other questions about question 2? Alright, if not, we'll move on to question 3. This is probably the most difficult of them, and I believe Anand said you have to get all of them right to get the marks. I believe that's what it is. So you'd have to pick.
If you get one wrong, you lose all of it.
I think that's what it said.
Yeah.
I think that's what he said last year. You can confirm it with number, but I believe that's how it works. So if you get 2 and 1, he might give you like one of them. But if you get 1 and then 2 wrong, you might not get the marks.
Yeah, in this one, you still get all those marks.
Yeah, potentially. Okay, so if you've had a read through, pretty much the first 2 a couple, the second 2 a couple, and the third 2 a couple. So I'll take a look at the first 2 to start with. So they're pretty much the inverse of each other. So statement A says for control volumes, the PV term added to the energy flowing in or out of the control volume represents an abbreviated form of the ideal gas law. And then B says for the control volumes, the PV term added to energy flowing in or out of the control volume represents the flow work needed to push mass in or out of the control volume. Does anyone want to yell out whether they think those statements are true, whether one of them is true, whether neither of them are true? So I'll just jump in. So B is our correct statement here. So I'm not sure if they've run through it, but the way it was explained to me is enthalpy is the energy required for mass or flowing mass to occupy that volume. So I've got a little drawing here, which hopefully, I'll give it away. Anyway, we'll go on. So we've got our control volume here. Yeah, that looks better. So we've got our control volume here. and we've got some fluid flowing, and basically the whole point of the enthalpy is what's to stop that fluid flowing. Well, that fluid has some energy which forces its way into our control volume, like pushing the mass in front of it, and forces our way out of the control volume. So that's why B is correct. So that PV term, so remember that enthalpy is U plus PV, that PV term represents the flow work that our mass requires to enter or exit our control volume. Right, C and D is a bit easier, giving away the answer. So we had an ideal diesel cycle has isobaric heat addition, while an ideal Otto cycle has isochoric heat addition, and that's due to the way they're designed, or an ideal diesel cycle has isobaric heat addition, while an ideal Otto cycle has isochoric heat addition. And so is it due to the way that the piston cylinder, in one case it's isobaric, in the other one it's isochoric, or is it due to the chemical reactivities that one case it has to be isobaric or one case it has to be isochoric?
Is that closed? Going in and out. No, that's flow B. That's flow A.
Alright, does anyone want to yell out which one's the correct answer or why they have reasoning behind their answer? Yep.
The petrol needs to have a spark to ignite in the Otto cycle, whereas the diesel ignites at a certain pressure.
Yep, perfect. So I've given a little summary down here. Yeah. So you can see we have isochoric ignition and then isobaric ignition. But the key part here is we had an ideal spark ignition or an ideal compression ignition. So our diesel will ignite at some pressure, where our Otto cycle requires spark. If there's anyone who's mucked around with cars, pretty sure that's what the spark plugs are there for, and that's why you can't put diesel or petrol in your other, like in the wrong engine, otherwise you don't get complete combustion, get stuff like engine knock. And then finally you have E and F. So an isolated system, so we can't exchange mass or we can't exchange energy. The entropy and the energy of the system cannot change, or F says for the same scenario, we can't change energy, but we can change entropy. Does anyone want to yell out what they think? F, and why F?
You can do work and still not increase entropy, but you can increase energy.
So that's, but does the energy of the system change when you do work?
Yeah.
Not quite. The energy is transferred. So we have no heat or mass float in or out of the system. It's a weird question, but it pretty well comes back to your first law and your second law. So our first law says that the total energy is conserved. So if we have a closed system and we're not, if we look at it state 1, state 2, we have the same amount of energy, whereas the second law says that our entropy either has to remain the same or increase. So if we look at state 1 and state 2, we need to have the same energy, but at state 2, we can have high entropy due to some process that's happened. It kind of does come down to how you look at these things. So what this comprises 14 marks, and then ideally you'd only want to spend like 15 to 20 minutes on these questions, if that, because obviously when we get to this one, you can see we have 36 marks and it's a much bigger question. But does anyone have any final questions on our multi-choice section?
Oh, really? Huh? Yeah, I've seen him in the exam explaining it to me. Can he sit in the exam next to me and tell me how to do the questions while I'm
I'll
writing?
run us through question 4 now. So as you can imagine, this is the most important question for your thermo part. If you're not aware, your hurdle is 40% of the marks in thermo and heat transfer separately.
Oh my god, no way. That's so funny.
So as you can see, you need 20 marks from thermo, 76 that are contained in this question. If you really struggle with the cycle questions, you're going to be in trouble. That's all I can say really. Anyway, so we have a graduate engineer, and you're working on a combined cycle gas turbine plant, and we have a mature gas turbine, so that's basically like this cycle through here. And we're told the net power is 300 megawatts. We have a compressor ratio of 20, turbine inlets at 1450 degrees Celsius. We enter the compressor at 300 Kelvin and 1 atmosphere, and then it tells us we can make some assumptions about some ratios and SCPs. So you're given 3 diagrams here. So we have this first diagram on the left, so we have compressor, combustion chamber, gas turbine, and then where we reject our heat, and in this case, where we reject our heat is actually our boiler for our Rankine cycle. So we've got a pump, a boiler, in this case our heat's coming from our gas turbine, and then we have a steam turbine, and then we have a condenser. So these cycles are linked together, and you can see that again in our entropy temperature graph. So I'll point out one key, I'm not sure if it says, but what you're meant to pick up is that we have vertical lines here, so we must have isentropic compression and isentropic expansion in both our compressor, turbines and pump. And then finally you have this last graph over here, which we don't need at the moment, but we will come back to that later. So, like I said, they'll step you through these questions. So, part 1 is just looking at our gas turbine. So we're given all this information up here, and then overarching we have 375 megawatts of work. So first up we want to know the back work ratio. So we want to know the ratio of our work in to our work out. So first thing we need to know, we're dealing with the gas turbine, and based off, this is what we're given, based off what we're told, we need to know that we're dealing with an ideal Brayton cycle, and because we don't have data on this, we want to use some ideal gas conventions, specifically our isentropic conventions, like this. Now I'm not given anything about volume, so really we just want to look at this equation here. So if we want to find, well, at the moment we don't have our mass flow, so we can't find our absolute work, but we can find our specific work, so that'll come out in kilojoules per kilogram. So what we want to do is to find the work across the compressor. We know it's going to be Cp delta T, we're given T5, so we want to find T6. So we can just use this relation up here, and we can plug this in. So if you multiply it by T5, we know that our pressure ratio is 20, and then we're given this is K minus 1 over K. Just be mindful we want to use Kc, the K across the compressor. And then we can find T6, it's pretty straightforward. And we can repeat the same process to find T8, so that's our outlet to the turbine. Built into our assumption that we have an ideal Brayton cycle, we have isobaric heat addition and isobaric heat rejection. So knowing that, we start at 1 atmosphere and we go up to 20 atmospheres, and then we must return to that 1 atmosphere. So our pressure ratio through the turbine is just 1 over 20, so we can plug that in and we get T8, and then from there we can find our work in to work out ratio, which is just our Cp delta T, making note that we have 2 different CPs for our compressor and our turbine. Alright, sweet. Yeah, so we can just plug in, like they give you the equation up here, we can just plug it in and solve for our back work ratio. Any questions on this? Alright, we can move on. Alright, so now we want to find our mass flow rate. So we're given the network, yes.
Sorry, just going back to that, how did you go from the your ideal gas rearranging the isentropic assumption to the get the RP term in those equations for T6 and T8?
It's given.
Is it?
Oh yeah, so we're given RP equals 20. So we enter the compressor at 1 atmosphere and we exit at 20 atmospheres. And then because we have isobaric heat addition and heat rejection, we must come back down to the 1 atmosphere. So that's why across our turbine it's 1/20.
Yeah, okay. Thank you.
And then, like in this case, T1 is just multiplied up across. Yeah, so this T1 would be multiplied up here.
Yeah.
Like that's how the T5 gets here and T7 gets here.
Okay, thank you.
Alright, so now we want to find our mass flow rate. So what we can do is, because we know our gas turbine produces 300 megawatts of energy, we can find the net work, or the net specific work, which is just our work out minus our work in, which basically is just this denominator minus this numerator. And we determine it to be 580.9 kilojoules per kilogram. And then we know that our absolute work is our mass flow rate times our specific work. So you can see all we have to do is divide our absolute work by our specific work, and we get our mass flow rate, which comes out to be 516.43 kilograms per second. Alright, and then finally we want to know our thermal efficiency of our gas turbine. And thermal efficiency is just a measure of how much work do we get back from the heat we put in. So this comes back to the theory of heat engine. So we put some heat in, expecting to get some work back. So it's just simply the ratio of work we get back from the heat we put in. In this case, they tell us to use the CP of the compressor. So we can calculate QH by our mass flow rate times the CP of the compressor, multiplied by our temperature difference across the boiler or our combustion chamber, which is T7 minus T6. And we already know our net work, so if we divide those, we get 49.7.
That's all simple.
So I'll leave these up here for a few moments. If anyone has any questions, feel free to ask now.
That's T4 minus T6. T7 minus T6.
Incidentally, need to join this
Oh yeah, that makes sense. Go for it. Yeah, I'm actually pissed off that I didn't realize there was like one mark there. That was the only thing that I. Why is it that? Oh, because it goes back into the atmosphere, so then it has to be atmospheric pressure. Oh. It's not because it's like to hide the area. It's just because it goes to the atmosphere.
So K is the...
Because that's fine. But what if the turbine wasn't blocking?
So it's KC on the compressor side.
So like if you put the atmosphere is 1 you have 20 in RPM pressure, you put 20 in PSI into the turbine. What if the turbine only reduces it to 5?
No one has any formal questions about part 1?
You know, like the pressure at 9 and then fucking pressure at 8. Because it's constant.
Alright, so we'll move on to part 2. So our goal in part 2 is to solve our ideal Rankine cycle. So we're told here it's an ideal steam Rankine cycle. We're given the condenser pressure, and we're given the turbine inlet pressure and temperature. And then we want to go from there. So before we get into anything, yeah, basically we just need to know it's an ideal Rankine cycle. So coming back to our graph here, what's important to note is state 1 is a saturated liquid. So we know the pressure, we know it's a saturated liquid, we can find everything we need to know from there. We're given all our properties about state 3, and because we know it's isentropic, using our entropy relation, that's how we can go ahead and solve for all our values at state 4. State 2 is a little tricky, and I'll go through how to solve that. But pretty much we know that our change in entropy will be equal to some relation we've used. Yes?
Can I see what you subbed in for part C of I? Because we've just like done it and we get 56%, whereas you got 49.7. So I know we're just using the wrong CP values.
That's crazy.
So use the 1.005 for the QN.
That's right. Have you done this paper yet? No, but I attempted it. Give it 6 stars. That's because.
Yeah, we got 56, but maybe we're just
56. I've just written these based off the solutions I was provided by NARM.
So the CP value is 105. Is that what you said?
Yes, that should be the one that was given up here. Yeah, 1.005.
It's Robin Stain.
So we've definitely got
Robin Stain wrote that.
Yeah, we're given T7. So T7 is definitely. You've definitely got T7 and T6, correct? Yeah. Alright, that's why. So the method's correct. We may have the wrong answers though, but that's still the correct formulas and correct working to get there. Right, so anyway, we'll come back to part 2. Alright, so yeah, we're dealing with the ideal Rankine cycle. So we basically know that P4 equals P1, which is 10 kPa, P3 equals P2, which is 4 MPa, T3 equals 450 degrees, and T1 and T4 are going to be at saturation temperature. So what we want to find the network per kilogram of so we want to find the network through the turbine and our quality at the outlet. So basically we just want to find our work across our turbine, which would be H3 minus H4. So first we want to, we should also know that the actual work coming out of our turbine is 75. If the whole cycle's producing 375 megawatts and the gas turbine produces 300, our steam should produce 75 megawatts. So our network's the work through our turbine, minus the work through our pump. So basically, from here, we're just set up to solve the cycle. So we know H1 is equal to the enthalpy of a saturated liquid at 10 kPa. We can assume an incompressible liquid, and then we can solve for the H2. So even though we don't know the work across the pump, we can ignore this and just focus on these two aspects here. We're assuming there's no temperature change across our pump, so that term goes to 0. And then we're left with H2 equals VF times P minus PSAT plus H1. So this VF would be our specific volume at 10 kPa for a saturated liquid. And then this is 10, and this would be 4,000. So be mindful, we typically work in kPa, not MPa, so you have to convert over to kPa. From there, we can solve for H3. H3 is as simple as reading off the tables, just like we did for H1. And then we can assume we have some isentropic expansion. we know S3 equals S4. From there, we can solve for our quality at outlet. I don't think you might be given this formula. If not, hopefully remember it from MECH1500. And then we can use this equation over here to determine our enthalpy at state 4, which comes out to this. And then we get a network of this. So we can plug in our values up in here, and we should get this answer. Hopefully it's correct. Right, and then part B is determining the mass flow rate of the steam. So this is just like part B of the previous section of the question. We know our absolute work and we know our specific network, so we can just rearrange to find the mass flow rate of the steam. And then finally we want to find the thermal efficiency of the Rankine cycle, which again is just our network divided by Qing. In this case, I've used the specific work. You could do that in the previous question as well because our mass flow rate terms would cancel. And then our Qing is just H3 minus H2. And this comes out to 36.02. Again, hopefully that's correct. If not, the process is always correct. I'll leave this up here for you guys to get notes down.
So it's
Any questions about this part of the question?
Part 1 and part 2 are the exact same thing. It's the exact same, but it's worth 26 miles on 100 mile per hour. Or is it even 100 miles? I have no idea. I mean, obviously you're not calculating this, but like, this one you're just calculating enthalpies, and this one you're just finding, like using isotropic relations.
It's easier than before.
It's a lot easier. Yeah. I'm just retarded because I got stuck on here and it said C for the rest.
We don't have that luxury during the exam. Like if you miss this question, you just fail the course.
That's so funny. That actually, imagine if you just went blank for like the thermo, got 39% and then failed the entirety of the 3400.
Even if you only got half of one of these questions right and none of the other ones, you would still fail the whole course.
No, but if you got this one, you'd get this one. And I don't know, I would read this one.
The hurdle applies to both.
No one has any questions, we'll move on to part 3.
40% from this.
If you failed, if you got 0 for this.
What you would have noticed is we've
That's
pretty well gone through and
If you got
solved our
100
gas
for this,
turbine,
you're done.
we've solved our steam cycle, but we haven't really touched on this heat exchanger here, which is part 3. And this is kind of this is pretty well the extension of the question. So parts 1 and 2 followed each other pretty closely. But now we want to look at this heat exchanger and what does this do on the cycle. So pretty much we want to estimate the temperature of the air and the gas turbine exhaust at like, basically we want to find T9 and then we want to find this temperature pinch point, which is pretty much, I believe the pinch point is that temperature when you begin, or I'll give it away here, it's the temperature when you begin to boil the water. So the big connection you have to make here is basically once we get to this temperature here, we've started boiling the water pretty much. So it's weird, like this graph here, if you were to plot this in time, obviously this second line would go in the opposite direction because our water's increasing in temperature as our gas is decreasing in temperature. So what you need to know is this pinch point temp is when our water starts to boil. So, solving for T9 is pretty straightforward. So we can do, basically all we need to know is that the heat we reject from our gas turbine cycle goes into our Rankine cycle. So if we do the energy balances across them, we should end up with this relation. And then we can solve for T9, so whether you want to rearrange them or you can just plug in values and rearrange from there.
What does that say?
And then this is what I was commenting on before. So when we switch to looking at the temperature at the pitch point, looking at a heat transfer diagram, it corresponds to when our water gets to boil. So from that, we can create this relation. So we're going to go H3 minus HF at 4 MPa because we've raised the pressure of our water to 4 MPa, and then we're looking at the energy transfer specifically from when it begins to boil. So it's a saturated liquid, and then it's between temperature 8 when we when we enter our heat exchanger, and then temperature pinch point, because up until that point, after that point, due to inefficiencies in the cycle, we can't reject any more heat to our Rankine cycle. So just like we did with all the other ones, we can plug in values or we can rearrange and we can solve for pinch point. But pretty much what got everyone stuck was this conceptual part here, in that you had to use this heat transfer diagram. I'm not sure if Anand showed you this. I don't think we saw one last semester or last year, sorry. But that's pretty much what got everyone stuck. So following from that, now that we have the temperature at the pinch point, and now that we have the T9, we can determine the heat rejected, or the total heat that's rejected across the heat exchanger, whether that's absorbed or not. And that's just our energy balance from state 8 to state 9. So it's N, CTT, T8 minus T9, which should come out to 208.23 megawatts. And then we can just do the efficiency of the whole cycle. So we're told the whole cycle produces 375 megawatts. That's why I've got that 10 to 3. And then the only heat we put in is in our combustion chamber up here. So make note of that. I think what they're trying to do is trick people up into thinking, there's Qin in the Rankine cycle, but that Qin for the Rankine cycle is already within the cycle because it's just exhaust heat or wasted heat that wasn't converted into energy through our gas turbine. So we should only have one Qin term, which comes out as this, and we should end up with 71.04%. Do we have any questions on part 3? If not, I'll leave this up here so everyone can take it down.
Immediately, I'm not getting this question in the exam. There's no way of figuring that shit out. Because how the fuck are you supposed to do that? That the pinch point is where the water boils from that diagram. Like, I've never heard the word economizer before. Like, what the fuck?
Is that T7 minus T6? On the bottom. Under 375 by 10.
Oh, yeah. Oh, yeah, no, it would be because the only energy that's going in is in the combustion. Yeah, I would probably model that as well.
That's your heating, so that's looking at.
I would definitely just say, it's the heat exchanger.
Yeah, no, that makes sense because that's just your heating. You're looking at Q in over there.
Yeah, it makes sense. Is this way? Is this way? The whole thing? Oh, it is like Yeah, so for that question,
Is
I've already
everyone
got
happy to move on to the next question?
maybe
Or do you still have some ideas or thoughts about this question here?
He
Yes.
does it both.
Matt's just asking.
Oh, that pressure, that pinch point temp, that is 576.03 kelvins. Is that the correct answer or?
For passing, what temperatures do you use?
He was.
Oh, T7 and T6. Yep, does everyone understand part 3? We're getting a few head shakes. So I'll try and go through it one more time. It's pretty much, you could pretty well solve everything except for that pinch point temp, because that's not related. But as I was saying, this plot's sort of deceiving because it's just temperature and heat transfer. So as you could imagine, as our exhaust gas decreases in temperature, our water must increase in temperature. But I think it's intuitively it's easier to understand it if it were to go with time. So as our exhaust gas comes down, and you can see it here, even though it's not to scale really, pretty much the pinch point occurs when we begin to boil our water. And we know that because it's a giveaway through this flat line here. So here we're a saturated saturated liquid, and here we're a saturated vapor, and you can see that corresponds to our pinch point temp. So the pinch point occurs when our water begins to boil, and then the amount of heat we can transfer is the difference between this temp and this temp, and this temp and this temp. So this remaining bit here down to T9, and this remaining bit here down to T2. That's not included in our energy balance for that part of the question. If you want to know more about this, I'm sure your Thermodynamics textbook has a section on combined cycles, because I believe I looked at it and then skipped over it. Yeah, that didn't work for me either, so. And then anyway, we have part 4. So Anand's dropped the bonus question if you want to pick up some marks. It's cruel because it's once again related to that pinch point temp, so I don't know who was trying to help.
It's like shaking candy, like over a baby that can't reach it. You know what I mean?
Yeah, well, people get stuck at the pinch point, and then he goes, you get more marks if you solve for delta PP, where you need the pinch point temp started. So anyway, under the assumption that you know our current pinch point temp, we can go ahead and solve this. So they say that the minimum is 20 degrees Celsius. And pretty much what we're going to do is we're going to do a comparison that if we were to use 20 degrees Celsius or our current pinch point temp, what modifications to the cycle would be required, specifically in how much work we can extract from the Rankine cycle. So at the moment, our difference in temperatures in our actual cycle comes out to this 52.52 Kelvin, or you could replace that with degrees Celsius. It's just that I've subtracted kelvins from each other. So basically we know our pinch point temp is 576.03. So knowing that our delta PP is 20, our minimum pinch point temperature is going to be 543.5 kelvins. So because our pinch point temp's been dropped, we're actually exchanging more heat. But because we're fixed within our cycle, what's the only way to exchange more heat through that process? Did you yell at the answer? Also, think back to your refrigeration prac. How did we increase heat transfer? Yes, exactly. So if we're rejecting more heat through our heat exchanger, we're going to need a higher flow rate if we're operating at like fixed temps. So knowing that, we can use this energy balance here, the same one that we used to find our pinch point temp, except now we're going to find our new steam flow rate. So that says ST max, and we find that it increases to 73.94 kilograms per second. And then we want to find out how much more work can be extracted from the cycle. So we want to calculate our maximum net work, which comes out to 83.5 megawatts. And if you remember, we started with 75 megawatts, so that's like 8.5 megawatts extra. If you wanted to, you could extend on that. You could recalculate your cycle's efficiency. That might have an increased effect. I'm sure at this scale, if you were to actually do this in like a professional aspect, they'd be very happy for an extra 8.5 megawatts. So yes, if Anand's nice, he might give you a bonus question in your exam again. I just recommend solving all the ones you meant to solve instead. I'll leave this up, and then we can flip over to heat transfer. Is everyone happy with what I've run through in thermo? Yes.
Could you just briefly explain why, like, you use the saturation temperature and then the fluid enthalpy for the calculations using the pinch point temperature?
Oh yeah, that just relates back to remembering our pinch point occurs when our water begins to boil. Right. So we have to do the energy balance from here to here. So if we can't use T9 and T2, we have to use this temperature here, and then the trick was you should see it's flat, so we know it's beginning to boil. So it must be saturated with
because it's on the steam pressure.
1 million% accurate. If not, guess what? I'm glad.
Yes.
I've said it. You want up on the I'm done.
Sorry, can I get everyone to quiet down? There's a question.
But then you just assume one, so you can keep going with the work. And did you get any marks?
Potentially. Admittedly, I did not get the pinch point temp, but you can see B and C don't require the pinch point temp. So pretty much you're only losing out on like 2 marks or something. Like you could imagine the first question might be 3 marks for finding each temp or something. So if you miss out on the pinch point temp, it's not really holding you back. Again, that's the whole goal. Like this question was structured to step you through the solution, instead of just asking you to solve for the overall efficiency of the cycle, it stepped you through to find that. If everyone's happy, we'll switch over to heat transfer.
You say tutoring? Yeah, like tutoring this course. I'm just thinking about it. I'm probably gonna get shit marks, so I won't do that.
As you might have expected, the exam's set up with half thermo, half heat transfer. In the case of this last exam, if you haven't had a look at it, it's set up the same as thermo. So we have 3 multi-choice questions and then 1 working question. Again, the multi-choice questions, they shouldn't take you too long. They should be like 5 minutes each. Some of them are really easy in terms of like explaining things, and then some of them are more difficult where you're actually going to work some things out.
We have 3 people. He just said that he was giving us tips for our heat transfer multi-choice. If you have any? Yeah.
Oh, if I haven't mentioned it already, definitely take a look at your formula sheet. So those isentropic relations I was using, that one, That's given, basically all your stuff's given here. Yeah, you're given that equation if you have a mixture. Given all your COP equations, given all your efficiency equations, given all your power cycle stuff.
Well, there's no extra.
Definitely make use of your
about that day.
formula book. If you don't remember something, just look through your formula book and hopefully you can find it.
So what have we learned since the midsummer?
Psychrometry, refrigeration.
So we'll get into the heat transfer.
We had this house, we just learned
So question one, we're going to evaluate two options for heat exchangers. So currently we have a parallel flow, but they're thinking of replacing it with a counterflow design. We have the same operating conditions, so they both have the same specific heat. They both have water entering at 90 degrees. The flow rate of 1.5 kilograms per second, and our cold stream is at 25 degrees with 0.9 kilograms per second. And we're given a heat transfer coefficient and surface area. Does anyone remember their heat exchanger equations?
Top of my head, yeah, good. Something's better than a chair.
Alright, so heat transfer is pretty good because you got such big equations. They pretty well give you all of them. So if we scroll down, we've got our heat exchanger equations here. So we've got counterflow, then we've got parallel flow, exactly what we need, and they even give you what NTU is, and they even tell you what this little c is. So pretty much everything's given to you, it's just up to you to default, know what's useful and what's not useful. So in this case, we're looking for effectiveness, and are we going to have a change in effectiveness? And if we do, what is the change in effectiveness? So the first thing we want to go through is we want to get our heat transfer coefficients for our hot and our cold streams. And then we have like our heat transfer coefficient ratio. So just remember it's mass flow rate times Cp of your hot stream, and the same for your cold stream. And then your ratio is just your hot divided by your cold. And then we've just also got to take note of Cmin. So obviously Cmin in this case is Cc. And if you don't remember that NTU formula, it was given to you here. And this U in this A, so this U is your overall heat transfer coefficient, and A is your surface area. That was given to you as well in this question. So we can solve for NTU, and then if we come back, we've got NTU, we've got C. So pretty much all we have to do is pick the equations. So C is 0.6, so we're going to use this equation. Pretty well, all you do is you just plug in your values for these two equations, and you should end up with these answers here. And then we can see our answer is going to be A. So if we change from a parallel flow to a counter flow, we're going to have slightly increased effectiveness. And how much more effective is it? 0.05. So that's a pretty nice question to warm you up. So then question 2 is our conceptual one. So we want to describe natural convection and forced convection. And what's the difference between these two? Which one has a high heat transfer coefficient and why? And then give us some examples. So basically it's like 1 mark for defining them, 1 mark for what has a high heat transfer coefficient, 1 mark for an example, and then 1 mark for the difference. Does anyone want to yell out what natural convection is?
It's like through density changes due to temperature variations.
Yep. So natural convection is just related to buoyancy forces. So our air naturally has a temperature gradient, and depending on the temperature, density changes, which affects your buoyancy forces. So like very slowly the air circulates. And then what's forced convection? Anyone want to get at what forced convection is? What's that? Yep. So our flow is then driven by something. So there's some like pressure differential that causes our flow to happen. Which one usually has a higher heat transfer coefficient? Natural or forced?
Forced.
Yeah, forced. You would have seen that in all your questions. And then what are some examples? So there's like hundreds of examples. The one I thought of immediately is if you ever have like hot coffee or hot tea, you can either leave it on the bench and it can cool down by itself, or you can stir it. And when you stir it, you'll find things cool more. You can do that with a cold drink as well. If you put ice in water and you let the ice sit there in the cup, slowly the water will get colder. But if you shake it around, you can sort of speed up the mixing of the cold and hot fluids, and you'll get a colder drink faster. So there's hundreds of examples you could give. Again, that's a pretty straightforward question. And then, specifically why our heat transfer of our forced compared to our natural is typically we have a larger velocity. Everyone happy with that?
Do you reckon that's half a page? Oh no, it's meant to be maths.
Yeah, max half a page. Yeah, don't waste your breath on these. I'm sure the markers don't want to read them either.
True.
Okay. So this question here, this is interesting. This one's really basic, but lots of people got it wrong. Alright, so we have a very large heated plate with one surface insulated and one surface is not insulated. So pretty much we're only transferring heat throughout one side of the plate. And we leave it in air, and the air's got lower temp than the plate, so obviously heat transfer from plate to air. Do you want to face the plate up so that it can interact with the air? Or like, I guess an assumption is like, do we want to place the plate on the table? If we're trying to decrease the temperature, if we're trying to maximize heat transfer, will we have the hot side up or the hot side down?
Hot side up.
Does everyone agree with hot side up? Yeah, so hot side up.
How do you get that?
There's definitely multiple ways you can think about this, especially in the drawing of the solutions. It's a bit weird. They've almost drawn it like the air can only get to one side. It's a bit weird. But if you sit the plate with hot side down on this table, it's probably not going to conduct heat through it as well as the air would. And then as well, the table's going to get really hot underneath the plate. And we know heat transfer is driven by a temperature differential. So then you're going to decrease heat transfer. So if you sit it up, we're going to get faster heat transfer initially because we're going to get convection instead of conduction. And then because we have air circulating, we can usually get air that's always at a much lower temperature than what the table would be. So I asked you to draw a diagram as well. So pretty much the diagrams you're expected to draw is something along the lines of this. So like I said, the ones in the solution are a bit weird. It's almost like there's no air underneath. But basically what they're trying to show is, like, having the hot plate down is just an obstacle. It just impedes heat transfer.
Is it basically wanting us to say that there's no conduction to the table? Because otherwise, wouldn't it conduct much faster to the table rather than convect in the air?
Potentially, but then you do end up with that issue of the table getting really hot, and then you don't really get that heat transfer. And that is that's the way I interpret it, but then when you look at this drawing that they've supplied, it is a bit weird in the sense that it's almost like an air can't get to the bottom of the plate. Yes?
I thought it meant like your plate's like floating in air.
Yeah.
And if it's upside down, then your buoyancy forces are actually stopping natural convection.
Maybe.
Because your air's not circling around because it's at the next point.
Yes, that's a very good explanation of that as well. That's probably what they intended it to think of.
That's getting regrets from us.
Anyway, don't say plate down, please. They asked this question, don't say plate down.
No, that
Look, there was many discussions about it after we did the exam. Anyway, so we had 3 pretty simple questions to get through. You should be able to smash out 15 marks right there. You're going to need it, to be honest. Not really. Not really. You get 4 marks for sketching the systems. You get 4 marks for assumptions.
English exam.
Anyway,
Yeah, I was just going to be like,
if you
even 16 mark question.
reasoning stuff, it's just simple marks. Give yourself the best chance of doing well.
They're going to get 16.
But pretty much we come into question 4. It's a bit of a weird question. So if you read it, we have a Teflon tube. They give us the conductivity. It's got a 1 radius. Some air at some temp. We have water flowing through it at a lower temp. We have a convection coefficient, except in this question we have some heating tape wrapped around the pipe that supplies a heat flux both in and out of the pipe. So I think that was the extension of the question. Because when you'll see in the diagram, heat transfer goes both ways.
They're just 2 real questions that are a little bit complex.
This over. Yeah, you end up with a diagram like this. So we have our ambient air, we have our heat transfer coefficient off the pipe to the air. We have our water flowing through the pipe. It's at this flow rate, it's at this temperature, but then we have this heat flux that's going in and out of the pipe, and that's at 2,000 watts per meter squared. And then they also expected you to write down your radii. So basically all information given up in part 1 or in the question brief, they want displayed in some way on your diagram. I'm not sure if Amid gets you to draw diagrams, but Caroline, who took this course last year, did. I think it's a very good tool. It can help you visualise how the heat transfer is going. I feel like heat transfer is a lot more intuitive than thermo, which can be helpful in some cases. But then obviously you have some pretty in-depth and wild equations to use. Right, and then the next part was some assumptions. I've used some abbreviations here, but pretty much your standard ones. We want steady state, we want a fully developed flow, we want one-dimensional conduction, so no matter where we are on the pipe, conduction is constant. And then we want to assume no radiation. Get that out of here, we don't want to deal with it. And then finally, there's one that's a bit more nitpicky, and that is the tape has no contact resistance, and the tape has no thermal resistance itself. You'll see this helps in the next part of the diagram, the next part where we want to sketch our heat resistance circuit. Alright, so we end up with this circuit. So starting inside and working out, we have the temperature of our water, then we have the heat tape sending some flux into the water, then we have the convection from our water to the inner surface of our pipe, and then we have the conduction through the pipe, then we have the outer temperature of the pipe, and then we have our convection from the outer surface of the pipe out to the air. So our Q dot is added on the outer surface of the pipe, but then you can see it's transferred into the water and out to the surrounding table. And I believe they also did expect you to write these equations as well to show you understood what these resistances are. So they're simply just your convection, and then the middle one's your conduction, but specifically for a cylinder. So I believe they're given. Yeah, so you've got that one there, and then you've got these ones here. So you don't have to remember too many formulas for heat transfer, it's more so the process that you want to remember. Alright, so now that we have our thermal resistance network, we want to go ahead and create our heat transfer equation. So I believe what they've done is they've looked at the heat transfer from the outer surface. It's a bit weird, as you can imagine. So the heat added is equal to the heat that we project outwards plus the heat we project inwards. So the heat added is that heat flux multiplied by the area, and that is simply equal to the temperature difference between our outside temps divided by our resistance for the convection on the outside of the pipe, plus the outside temp of the pipe to the water, and our thermal resistance is going to the water. So like built into this is the implicit assumption that the surface temp, or the outer surface temp of the pipe is higher than the temperature of the air. If you just got a negative answer at the end, obviously you know that would be the other way around. I think it's a pretty safe bet though, because you have the heating table on it. So we'll come back to this, but pretty well all you have to do is just sub in these equations where necessary on the bottom, but we'll come back to that. So our next part is to determine the heat transfer coefficient for the water flowing through the Teflon tube. So what you would have noticed is up here we're given everything except the HI, and we can't solve this equation yet until we get HI. So we want to find all the properties of the water. Yep, so we use this table here, and we're at 290 kelvins. So they pulled this conductivity. You should have just got a different viscosity. Anyway, viscosity is pretty close. So then we've got the Prandtl number, which again is somehow different. There may have been some. Yeah. You could, except she's got the exact same thermal conductivity. You could interpolate, which would make sense. It just threw me off that she's got the exact same thermal conductivity. Anyway, we come to this table, we can interpolate for our properties. Yes?
Are we evaluating that film temperature?
Sorry?
Are we evaluating the properties at film temperature?
Yeah, so it was given to us as 290 kelvins. So we should be sitting around 15, 17. So she probably has interpolated, because that's how she's got a different Prandtl number. It's just, she's just taken that thermal conductivity.
2 pi, is that gamma? HK.
Right, so now that we have all the properties, we want to characterise our flow. So this, pretty much here, we're just going to do our normal convection problem. So we want to characterise our flow. So we want to calculate our Reynolds number. So rho VD on mu is our equation, but obviously we don't know velocity, and could find rho, but what she's decided to use is mass flow.
Surface area times H times Q. Oh, yeah. So come, yeah. Sorry. It's done. Yeah, just so
Right, so I believe up here you have to use EH,
Small Q is flux.
and we have this relation here. So it ends up being that.
Yeah, I love that.
It ends up that you can use this relation here. So you've got 4 times mass flow on pi d mu. And from there we find out that our flow is turbulent, which is important. So they've given us 2 equations down here. And now that we've classified it as turbulent, we need to determine which equation we'll use. In this case, we're told that the fluid is less than the wall, so this alpha is going to equal 0.4. So we can use that equation for our Nusselt number. But we're also told that it's equal to HLC on K. We can replace this with D, which is why I've got this 2 here. So we pick this Nusselt equation, and then we know it's HD on K, but in this case we're only given the radius, so we can use 2 times the radius. And then just plug all your values in and rearrange, and you should get a inner heat transfer coefficient of 2792 watts per meter squared Kelvin.
So finding the Reynolds number. Oh, so you just calculate the Nusselt number.
Yes. No, that K value there is what we've got for water. Yep. So that comes from the table, and then I believe the K value they give you is for the Teflon tube.
Is that your fouling factor?
Yeah, it's the K they give you for the tube.
What's the power of the Reynolds number?
Wait,
Where's it?
4 on 5.
it does say
Yeah.
Wait, no, H just AH.
Yeah.
Does it?
Yeah.
No, you're true.
You said I'll play back. I'll wind it back. I wish I just had like a voice recorder in my glasses or something.
Have you seen the Facebook programs on this?
Yeah.
Right, I'll
They
jump
kind
on
of shit
to
out there.
part.
Like they're just an AI assistant, like
Part
Siri.
F is pretty much what we've been building up to. So part F, we want to calculate the outside surface temperature. So we've got our energy balance from before.
Because they've
Now that we know everything, I've
Oh,
substituted in my resistances. So that's why I've got your 1 over H and all that. It's a bit of a mess, but what we find is that if you multiply both sides by 1 over 2 pi L, you can get rid of 2 pi L, which is why I've crossed it out everywhere. So you'll be left with R naught Q dot. What we do though is we divide the left hand side by R naught as well. So this R naught disappears here, and that's why we end up with an R naught over here. And then we get an extra R naught out the front here. And then once again, now that we know all the information, we can sub in our values and solve for TS. So this is going to be our 2000, that's the heat flux from our tape. We're given this, these are all given. The only thing we had to solve for was HI, which we solved for on the previous question. So we can sub in our values and solve for TS. If you wanted to, you could go ahead and rearrange it. But I think if you substitute all your values and then sort of simplify it through that, through summing them, they'll be happy with that. And then finally they want us to determine the fraction of power dissipated by the tape that is transferred to the water. So like how much of that 2000 watts per meter squared how much of that goes to the air, and then how much of that is conducted through the pipe. Ultimately ends up in the water. So what they've done is they've done the energy balance to find the heat flux out, which is just our energy balance using convection from the outer surface to the surroundings. Which comes out to be 207.5. So of that 2,000 watts per metre squared, 207.5 watts per metre squared is going out into the environment. So if we want to find the ratio of the flux that goes in, we can just do the difference in Q minus Q naught, or Q outer, divided by the total energy input. And we find that 90% of the power dissipated ends up going into the pipe. Everyone happy with that? I'll leave this up here so you can take notes. That concludes this exam. Does anyone have any questions about the exam? This one in particular? Yes. Oh, this energy balance. So through our thermal resistance network, I came up with, we've got this energy balance here, which was like the amount of heat added is the sum of the heat that ends up getting convected outwards and convected inwards through the pipe, which comes out to be this. And we've solved for these resistances in part C. So all I did was I took that equation and I just plugged it in. And then through some manipulations with some of the common factors, I've cancelled stuff out. If everyone's happy, I did have a request to go through question 4 of the 2022 exam. I don't have the actual solutions for it, I just have what I attempted. So the 2022 exam was set up like the 2023 exam. It was almost the exact same, except the thermo part was much easier. But in this case, we have a counterflow heat exchanger with a length of 1.5 metres, negligible heat loss to the surroundings. So we know that air flows at a rate of 10 kilograms per hour within the inner steel tube. We're given our diameters for our steel tube. And then we have cooling water that enters and flows throughout the outer annulus, and that has some diameter. And then they give us the flow rate. And then we have some fouling factors for our inner and outer surfaces. And then we have our entrance and exit temperatures. And then we have our thermal conductivity of the steel tube. So, once again, I think Carolyn wrote this up. So we start with a sketch. So what I've done is I've done like two cross-sectional views. So because we have a counterflow and it's an annulus, basically we have this inner circle, which is where our air flows, and then we have this outer circle, which is where our water flows. And we know that we're going to transfer heat from the air to the water, and then I've shown it this way as well.
These guys don't have any radiation.
Another thing I like to do is I just like to write down all the stuff we know at the start. We then want to list our assumptions. So I've assumed steady state, no heat loss to the surroundings, we don't have any radiation, we don't have any change in potential energy or kinetic energy through our water, constant thermal properties, and fully developed flow. The next part of this question is calculate the total rate in which the heat is to be removed by the heat exchanger. So we don't know the entrance and exit temps of the water, so we have to work off air. And it just comes down to a simple energy balance for the air. So like assuming an ideal gas, we can use MCP delta T. So we can determine our mass flow rate in kilograms per second. So we're going to have to transfer 10 kilograms per hour into kilograms per second. And we determined that the maximum heat that we can transfer is 0.978 kilowatts. And then we want to determine the heat flow, the temperature that our water exits at. So I make the assumption that we have a constant heat flux. So all along our heat exchanger, we're transferring the same amount of heat. I don't specifically remember why, but I think it's just, if you were to go through might be here, if not, you can look through your solution, your heat exchanger lectures, and there should be something on
They could just literally that's what it said. But like a two-star question could be like that's one question and that's one question and then that's one question. Or it could be so for short.
Anyway,
or it could be like that's
so we know that our exit temp is going to be our inner temp, and then we just have to add, basically we take this energy balance up here. Pretty much what I've done is I've taken this energy balance up here, because I know it'll be the same for the water. I've expanded out this temperature term to have T exit minus T inner, and all I've done is I've rearranged for T exit. So you can see we divide Q dot by MCP, gives us that term, and then we take our minus Ty across to the other side, and we get our exit temp here. I've made an assumption that we have a density of 1,000 kilograms per meter cubed, so we can just jump straight to kilograms per second, and I end up with 65.92 degrees Celsius as my exit. So we want to calculate the effectiveness of the heat exchanger. So what I've done is I've used this equation here, but I had to calculate my C max. So first you have to find your minimum heat transfer coefficient. So I looked at my water and I looked at my air. I can see my air is going to be my limiting factor. You can sort of tell that as well because its CP is lower, so it has less of an ability to absorb heat. And we end up with the maximum heat transfer is 1.652 kilowatts. We plug that in to our equation. We find out that 59.2% of our heat is transferred through a heat exchanger. Well, that's how efficiency.
How are you feeling?
And then there we want to determine our heat transfer coefficients at the inner and outer tube surfaces. So I've used this relation here, and we were told that the thermal conductivity of the steel tube is constant at 35 watts per meter Kelvin. And we're given fouling factors, so we can use these relations here. So now we just want to go ahead and characterise our flow. So I've gone ahead and calculated my Reynolds number. So I've got a standard laminar flow. So I can use this Nusselt's relation. I can calculate H, and I end up with my, this is for my outer surface. I end up with my outer surface heat transfer coefficient of being 586.41 watts per meter squared Kelvin. Right, and then from here,
Close with the head.
alright, so what I've done is I've missed this, but you can use this relation here because we've got U outer and we've got A outer. We can then go ahead and solve for U inner. I don't know how, but I've missed that. Oh, sorry, no, I haven't. And then I've used this relationship here, and I found my log mean temperature difference, and I've gone ahead and solved for U inner in this fashion here. So remember, it's your high temperatures from each flow minus your low temperatures from each flow divided by the logarithm of the high temperatures minus the low temperatures. And then we have this formula here, which comes from like your log mean temp method, and we can determine that our U inner comes out to be this. And then we want to compare the thermal resistances due to convection, tube wall conduction, and fouling. So simply all we have to do is just calculate all our resistances due to convection, conduction, and fouling. So we know if we're going through a wall, we want to use this relation here.
We did.
Yeah. We have a pretty high conductance through our steel tube, so our resistance should be low. Our convection through our water ended up being much higher. We can look at our fouling factors here, which actually ends up being pretty low. And then we can use this relation here to solve for H inner, which is not given. And then we've determined our total resistance through our convection. Yeah, so all this is just the sum of my outer and inner convection, fouling, and wall. That makes sense. Like obviously our convection through our water and air sort of limited compared to the conduction through the steel tube. Just intuitively it's much easier to heat up a steel pipe instead of water or air, so we would expect it to be the limiting factor of the highest resistance. And then that's when I gave up, or I couldn't figure out part H. Was everyone getting similar, like these are just my solutions from when I was preparing for my exam last year. Is that what everyone's sort of been getting for this question?
Oh,
Has anyone attempted this question?
I've got the same up to part D, and then I didn't attempt the rest, so I think we're on top of this. Yeah, I got up to E, now the same, and F.
Alright, so I'm right. I'm right.
absolute sweat.
Good stuff. That's pretty much it. Like we could take a look at another, yes.
Then what's the point of finding the DI video given the tables results?
Sorry?
The tables below should show like all the result number for each DI video. So what's the point of that?
What are you doing in this situation?
I use this one here.
Yeah, we're probably studying that hand.
The world
Alright, that would be your meter and energy cell number. So I think if you were specifically looking
Jesus.
Which I think this is what you needed to do in the end, when my friends and I were working through it. In the end, we ended up using one of these.
Is that it? Are we done? That's my cousin.
Yeah, that's it. Then yeah, I'm done.
Are we done? Off to BBT I go.